Hello there, everybody. So this is our asynchronous video lecture about the seasons. Maybe it might also be called Astronomy 5. I think this is the last thing before the astronomy quiz that you'll take. So make sure you watch this and understand it. Try to go quick because I know you can rewind, pause, whatever you need. So I'm just going to try to zip through with it as quick as we can. Seasons. So first of all, there's this little graph here. I'll put this in the OneNote so you can look at this also. All this is a graph of the sun's size, apparent size throughout the year, right? Apparent, how big it appears in the sky. All this stuff over here, if this doesn't make sense to you, it's really not a big deal. It's in 31 minutes, 20 seconds. You know, if you looked on the horizon, that's 0 degrees. Straight over your head is 90. That's a 90-degree angle, so that we have 90 degrees in there. Every degree is broken down into 60 minutes. Every minute is broken down into 60 arc seconds. Okay, and so that's what this is measured in. So the sun is roughly 30 arc minutes, half a degree in the sky, about the same size as the moon appears in the sky. It changes a little bit. It goes from down here almost down to 31 minutes 20 seconds up to somewhere almost 32 minutes 40 seconds. If that doesn't make any sense to you, it doesn't matter. All that matters is up here it's larger, down here it's smaller, so it changes its apparent size in the sky. Okay, so knowing that, and then it plots on these different days throughout the year, right? So on March 20th, it appeared to be that large in the sky. On August 10th, it appeared to be that large in the sky. Okay, that graph makes sense. So now that you understand the graph, take a few minutes here, look at the graph, answer these questions to yourself. When is the sun closest to the Earth? And how do you know? When is the sun farthest from the Earth? How do you know? What does this tell us about seasons and our distance from the sun? Pause if you want to think about that. So, what this tells us is this, or when is the sun closest to the Earth? When it's largest, right? We know as things get closer, they look larger. So, it's largest, appearing to be largest here, January, December, so in the winter time. When is the sun farthest from the Earth? Right here, end of spring going into the summer, because it's when it looks the smallest. So what does this tell us about seasons and our distance from the Earth? That they are not related to each other, right? Distance from the sun has no impact on our seasons. So maybe you already knew that. We bring that up because that's the most common misconception about the seasons. If you were to just go out and start asking random people of any age, probably the most common answer you're going to get for what causes the seasons is we're closer to the sun in the summer, farthest away in the summertime. There's lots of things that we could just look at. Well, the northern hemisphere has one season while the southern hemisphere is having another season. Well, that wouldn't make sense. If it was about the distance, everybody would have the same season, right? Okay, so then our next question should be, so then what causes the seasons, which is what this is all about. Here we have a picture of something called an analemma. This is a picture of the sun taken at the same time each day over the year. Okay, maybe noon, probably noon. It's usually analemma is usually viewed at noon. So this is just a graph of it. So we can see then over the course of the year, all we need to worry about is altitude here. We can see that some part of the year it's very high in the sky. Another part of the year is very low in the sky. Does that have an impact on the seasons? Maybe. So remember this. We'll come back to this. Some things to make sure we know about the Earth moving forward here. There's some very important latitude lines on the Earth. We've got the equator at 0 degrees, and we got the Tropic of Cancer, which is 23.5 degrees north of the equator. The Tropic of Capricorn, which is 23.5 degrees south of the equator. Those are easy to remember because they're in alphabetical order. That's how I remember it. Cancer, Capricorn, going from north to south. And then up here, the Arctic Circle, 66.5 degrees north. The Antarctic Circle, 66.5 degrees south of the equator. So there's a reason for all those lines. They're not just randomly chosen. They have to do with the seasons. We mentioned this already, I believe. So just for the sake of talking correctly, rotation is the Earth spinning on an axis every day, every 24 hours. Revolution is the Earth going around the sun for 1 year, and it'll rotate 365 and a quarter times as it goes around in that year. Here's our lines of all we really need to worry about here is latitude mostly. So our important lines of latitude, again, same ones we just mentioned. I guess we're just saying, make sure you know northern hemisphere, southern hemisphere. Primarily, when we talk about the seasons, we're always going to be talking about the northern hemisphere. When in doubt, assume we're referring to the northern hemisphere. Southern hemisphere is basically opposite, but mostly northern hemisphere. So the Earth isn't straight up and down. It has this vertical tilt to it, 23.5 degrees. That's why every time you see, the Earth, a globe of the Earth, it's tilted 23.5 degrees from vertical, right? And that's relative to the plane of the sun. We could go into, in class, if you ever want to talk about it, how there's no up and down in space. So how do we know it's tilted? And it's all relative to the equator of the sun, right? The equator of the sun comes out like this, and the angle that we are relative to that is 23.5 degrees from what would be perpendicular to the sun's equator, okay? Important. Notice how it's tilted 23.5 degrees, matches up with these, right? And if you add those two together, you get the full 90 degrees. So a lot of easy geometry here. So temperature changes with latitude and the season. So what we're talking about, why is the tilt more important? Always comes up the next answer. If people are already past, oh, we know it's not the distance from the sun, it's the tilt. Everybody says that. Probably a lot of you right now are already saying it's the tilt is what causes the seasons. We want to go a little farther. Why does the tilt have anything to do with it? Okay, so Earth's axis is tilted during northern summer. The light hits more directly, and in winter less. So what we want to then get into is what this direct rays, what this means here. So some of this is hard to visualize, especially in this remote learning kind of way. I'll try to show you some little animations and things, but remember, sun's real far away and much bigger. So we're talking about why is a tilt and more direct rays important. To get to that, if we were in class, we might do something like this on a graph paper. You and your partner, somebody would stand on it, put their foot down on the graph paper, trace it, and then you could count and you'd get the area of your foot, right? And then you could do this little thing here, your weight divided by pressure applied. So how much pressure you are physically putting on the Earth in pounds per square inches. And we compare it to air pressure, and what you realize is that you standing on the Earth there are actually putting less pressure on the surface than air pressure. So we'll talk about air pressure later, but it's just a column of air from the surface of the Earth to the top of the atmosphere, and that air is actually putting more pressure on the surface, 14.7 pounds per square inch in all directions, than you are by standing on the Earth, okay? The next thing we would do is then somebody stand on their tippy toes. Hate that, but I don't know what else you call it. So you're standing on your tippy toes and then trace your foot. I couldn't find a picture of anybody tracing tippy toes, so we'd measure that small area. So you can see that's a much smaller area. And now when we do the pounds per square inch thing, we find out that now, just by standing on your tippy toes, you're applying much more force to the surface of the Earth than when you're standing flat-footed, okay? So all that's happening is now you're taking the same weight that you are, and Instead of spreading it out over your whole foot, you're now compressing it, focusing it into a smaller area, right? And so now you're applying a greater force to that smaller area. Same amount of mass, but more force because it's focused in a smaller area. Okay, we can relate this to a number of things, like a bed of nails, sort of reverse, but it's the same idea. It's not a magic trick. Look at all those nails. So you're evenly dispersing your weight, your mass, your force over a whole bunch of nails. If you were trying to do that and you put your weight on, like 10 or 12 nails, oh, right, it's going to hurt a lot more. Same thing here. And this, you know, this one maybe is more obvious. I don't know how many people ever try to lay on a bed of nails, but you may have stepped on something sharp in your life. One sharp thing and you put all your weight on it, ouch, right? But if you could do this carefully, step on it, you're dispersing all your weight over all those nails. If you're careful, it's not going to hurt. Look at that. I don't know if you've ever gone out on ice before, but that's always the safety thing. If someone's broken through ice on water and you got to go out and save them, you disperse your weight, spread your weight out. Because if you're standing in one place, that's a lot of force on one little piece of ice, going right through it. Spread out like this guy, you can just scoot right across it because now you're putting a lot less pressure or force on all the areas. Okay. One more example. I know this is a weird one. I couldn't find a better picture. Um, get those high heels on you, and someone is trying to mug you, stomp on their foot. Think putting all that force of your weight, and then you throwing your foot down into a very small area. So significant amount of force thrown into that little tiny area there, as opposed to get a nice flat shoe on where it spreads it all out. Okay, all examples of all the same thing here. Now, if we relate that to a beam of sunlight, same concept. Flashlight. I have a flashlight here somewhere. This would be better if we were in class. So I could, shine this flashlight down, like straight down, and then as I tilt it, just like on there, you can see on my nice shirt, as I tilt it, it's the same amount of energy coming out of this flashlight, but now we're just spreading it over a larger area. So imagine maybe this is like a heat laser beam, and this is your arm laying down here. You would rather have this, right? It's the same amount of energy, but spread out over a larger area, so it's less intense. Okay, more highly focused beam. So the more direct it is, the closer it is to a 90-degree angle, the more focused and intense the beam is. Okay. Same thing with the sunlight. It's the exact same thing. So we're going to keep saying that this is the direct ray. As you move away from 90-degree angle, it's getting less and less direct. It's spreading it out over a larger area. So already, hopefully, you can think back to that analemma and realize what's happening here. When the sun's really high in the sky, we're getting a very direct ray. As the sun gets lower in the sky, either from noon until later in the day or seasonally, uh, those beams are spread out much more over a larger area, and it's not going to feel as intense. Again, something you've experienced your whole life. You all know this. You go out in the sun in the middle of the day, hot, right? That beam is hot. You go out, let's say it's summertime, and you're out there like noon or 1, hot, and then go back out, right before as the sun's setting, 6, 7, 8 o'clock, when it's real low, not nearly as hot. So the same thing applies seasonally. One of the seasons it's very high in the sky. Another season it's very low in the sky. And so right here, again, it's very far away. Hard to have a picture that represents that, but when the Earth is just like this, sort of straight up and down relative to the sun, if you're right on the equator, it's right over your head. You're getting a very perpendicular direct ray. And as you move away, it's getting more and more of an angle. Okay? And then at the North Pole, an extreme angle. So the sun appears right here. If you were looking at it, you'd be looking that way, it would look very low in the sky, and those sunbeams would be very spread out. As opposed to this, you'd be looking straight up to see the sun. Okay, here we're in the northern hemisphere, and for a reason we're going to talk about soon, we always look towards the south. We're way up here, right? So we'd be like, we're always looking towards the south to see the sun. It's never over our heads here in Towson. So it's all about this tilting, okay? So this is an important little diagram to understand. Sun, as we orbit the Earth, as the Earth orbits the Sun, it always stays at that 23.5-degree tilt, okay? So over here it's tilted that direction, it's still tilted the same direction. That's called parallelism of the axis. So it's important that everybody understands that. Let me see if I can. Let's get it in the right way. So it's spinning like this, and as it orbits the Sun, it keeps that same parallel. If you could draw every day, make a laser line through the axis, those lines stay parallel to each other all the way around, always pointing towards the North Star. So it doesn't do this, right? Okay, it just spins like this. The old globe doesn't spin too well anymore. Like, okay, that's important. Goes around, always keep that parallel angle. Okay, so what that means then, here we are in the winter, we're tilted, we're leaning away from the sun. Let me get my globe again. So now, over here is the sun. So these beams coming in, the sun is actually over top of the Tropic of Tropic of Capricorn down there. So if we're up here, we're getting very low angle sunlight. Also, one other very important thing, it's hard to notice here when we're not all together. If I were to rotate this, the sun is sort of hitting down here because we're tilted away in the winter. We are on this one here. So we're leaning away in the wintertime. As we rotate this for a couple days here, what we would see is that we're hardly in the sunlight, right? We spend, the light actually only gets to the Arctic Circle up there. And so we as we rotate, because we're so far north, we spend only about 9 hours on this one day in the sunlight. And the rest of the time we're in the dark, okay? Makes it winter time. And then as we orbit around, I'll show you a little animation of that here in a minute. As we orbit around, so this is our first day of winter called the winter solstice. And then as we go over here, this is going to be spring. So what's significant about the two equinoxes, that the Earth is still tilted 23.5 degrees, but notice it's not tilted towards or away from the sun, okay? Summer solstice is over here, tilted towards the sun. Winter solstice tilted away. Two equinoxes in the middle, they're both tilted the same direction, just not towards or away from the sun. So that's why we have the mild seasons, okay? This will make sense here. So this is 3 minutes long. We're just going to watch a little bit of it. So we'll watch a little piece here in a second. Those are things I want to show you, but I would encourage you to go to the PowerPoint and watch this whole thing. It'll explain a lot.
You know that Earth orbits the sun, right? And that it takes a full year for our planet to complete its orbit. Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year.
So notice right here, this is important. Notice the angle. So we're tilted away. The sun is hitting the Arctic Circle there. So the whole North Pole, this is our probably first day of winter, the winter solstice. So as we're leaning away, the North Pole, everywhere above the Arctic Circle there, as it rotates, it's going to be in the dark. Opposite for everybody south of the Antarctic Circle, going to be in the sun completely. So that's why the Arctic Circle is an important, significant line. It'll hit there on the first day of winter. It's the farthest it goes, and it goes all the way over the South Pole to the other side of the Antarctic Circle on the first day of winter. Opposite then on the first day of summer.
Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool, with short days and long nights. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun.
Still tilted, right? But relative to the sun, it's got a 90-degree angle. Makes sense? So on this one day, then, 2 days, either the spring equinox or the fall equinox, we rotate everybody on Earth. It's basically 12 hours of sunlight, 12 hours of dark for that one day. Thus the name equinox, okay? So the rest of the video is explaining that kind of stuff.
Day and night are...
There's this little simulator we can look at that I think. So that's what this is showing. So just check out here. It's showing light intensity for 3 different areas: Arctic, the Tropic of Cancer, and the equator. So very high, mid-range, and middle of the planet. Mid-range for the northern hemisphere, right? Notice, take a note, everybody, of the sun intensity, the light intensity at the equator hardly changes, right? So as the sun goes back and forth across the sky throughout the season, it's basically really no seasons at the equator. It's just a hot season and a hotter season, right? Where at the Tropic of Cancer, right in the middle there, it changes significantly. There is a point where the sun is directly overhead, the summer solstice, and then look at the light intensity there, the Arctic Circle. The sun is 0 at some point, and then notice where the sun rays reach to. That's why we have the Arctic Circle and the Antarctic Circle. So that link is in the PowerPoint. You can study that over a little bit if you need to. Going here. So if we're looking at hours of sunlight per day, so one thing important is that where the direct ray is hitting, it's going to be the hottest location. Second behind that is just hours of daylight. So the equator, these are average, right? Or I should say, on the summer solstice, 12 hours of. So on either solstice or equinox, the equator gets basically 12 hours of daylight all the time. Let's see, for Denver, that's close to our latitude. On the winter solstice, over here, when we're tilted away, we only have about 9 hours of daylight that day because we're tilted away from the sun. So we have a low angle sun ray, so it's not as intense, and then we're not just not getting as much sunlight, as opposed to the first day of summer solstice, where we're getting about 15 hours of sunlight. We're tilted towards, so as we rotate, the vast majority of our time that day is in the sun. Plus, we're tilted towards getting a more intense sun ray. Okay, that's why as you get closer to the equator, between the tropics, that's why people go south for vacations. Right, in the winter time, it's always going to be warmer there. All right, so if we run through these are just naming the seasons, the first day of each season, rather. So we have the autumnal equinox, somewhere around September 23rd. It's the first day of fall. You can call it the fall equinox if you want. About 12 hours a day, 12 hours a night. The vertical rays are right over the equator on that day. And that's that one there. Not always September 23rd. 20, 21, 22, just depends when it happens. And the important part is the sun's direct ray is right over the equator. So if you're standing at the equator that day, the sun is directly over your head. Then we have the winter solstice around December 22nd, 20, 21, 22. And this is for the northern hemisphere. We get about 9 hours of daylight, 15 hours of dark. That's why it's cold. And then the sun is way down over the Tropic of Capricorn in the southern hemisphere, right? So if you're at the Tropic of Capricorn, the sun will be right over your head, okay? So remember, the warmest point is where the sun is directly over. So it's at the Tropic of Capricorn on that day, and we are way up here, right? Like 39 degrees north of the equator. So we're far away from that. That's why it's colder. Plus, not much sunlight that day. Spring equinox around March 20th. Same as the other equinox, just on the other side of the sun. Right over the equator. Sun's direct rays. Lastly, then, wonderful summer solstice, first day of summer. 15 hours, right over the Tropic of Cancer. So on that day, then, if you're at the Tropic of Cancer, you would look directly up and see the sun. It could be right over your head. So we're too far north for the sun to ever be over our head. So if you think about it, throughout the season, throughout the year, the sun travels back and forth from 23.5 degrees, 23.5 south, just all year long, back and forth, right? So we're always looking that way to see the sun. Sometimes it's closer. So this, we could calculate how high in the sky it would be, and all you ever have to do is this is if you were at the Tropic of Cancer, it's going to be at a 90-degree altitude. So as you move away from that, you're just getting less and less. The sun goes down in the sky, just like if I was underneath this light at a 90-degree angle. As I get farther and farther away, the light goes down relative to how far back I move. So depending how far away you are, that's how high in the sky the sun would be. So we could take our distance that we are away from the 23.5. So we would say 39 degrees is where we live, minus the 23.5, right? And then subtract that difference from 90. And that's how high in the sky the sun would be. We usually do that in class. We calculate a bunch of altitudes like that. So last couple things here. We can look at this diagram in two different ways. Here's the sun, here's the earth orbiting around it, and then there's the seasons. And in case you weren't sure, snows in the winter. Or we could look at it like this. We flip it around. There's something called the celestial sphere that we use a lot for astronomy and stuff. And where we put the earth at the middle and imagine the sun going around it, which we talked about before. So when we are at the winter solstice, it's when we're tilted away from the sun. Okay, so that makes the sun really low in our sky. Summer solstice, when we're tilted towards the sun appears very high in the sky. So that's the top of the analemma that we talked about at the beginning of this. And then the very bottom of the analemma would be the winter solstice, right? We've talked about this before. This is the ecliptic. All the constellations would be along there, the path the sun takes throughout the year. So it serves us well also for the seasons. Lastly, reasons for the seasons. We've talked about the Earth's orbit. So it's an obvious one, but if we didn't orbit the sun, we wouldn't have seasons, right? If we stayed in one place for some reason, we would always have the same tilted angle, and so we wouldn't enjoy the seasons. Parallelism of the axis, that means all these lines of the axes of the Earth every day are always parallel to each other, so it always maintains that same angle all the way around the sun all year long. Lastly, the Earth's tilt, 23.5 degrees. So what we should add in here, what you make sure you know about the Earth's tilt, is the two things that it causes. One is it causes the location of the direct ray to change, right? Wherever's getting the direct ray, more focused heat, right? If you're at that angle, if you're at the location that's getting that 90-degree angle, it's going to be much more intense than anywhere else. So Earth's tilt causes changing location of that direct angle, the direct sun ray, and then it also changes how much daylight you get. It just stands to reason. If you are absorbing 15 hours of sun on the first day of summer, things are going to warm up more than on the first day of winter when you're only getting 9 hours of sun, not to mention the very low angle sun ray, not very direct. Spread out, unfocused beam. All right, so that's why we have the seasons. So now what you can do, there's a seasons in 3D Gizmo that you can work on now. Log in with your username and password. Yeah, play the seasons in 3D Gizmo using the seasons in 3D document that's on It's Learning. And it'll go through some specific examples of locations to compare it to. So that's the seasons. If you got any questions, you can bring them up. You may be watching this and doing this before the week where we have the optional meeting. So if you want to come in and ask questions, I'll be there if you want. Good. Don't worry about it. And then you have a quiz coming up after the following week. So have a good week.